Welcome and hello. This is a Powerside technical video and I'm your host, Chris Duffey. In this video, we're going to discuss power flow simulations and how they are relevant to you. So let's just dive in and get started. I have some slides for us prepared. And where I'd like to start is some history. I'd like us to take a step backwards and just review a number of things that have happened in our past, or actually before some of us were even alive. And let's take a look at that and see how some of the groundwork was done before us that was laid so that we can perform detailed power simulations today with extremely large networks. And a lot of that work was done for us by one particular engineer. So since the beginning, we had a need to know network conditions. We need to know voltage conditions, flow conditions within our network. And before digital computers, all of that modeling was done in the analog domain. And that consisted of creating an electrical equivalent of the power distribution system or the interconnected grid system, and then changing voltage sources and components within that model so that our results would change, our flows would change, and our bus voltages would change. And then we would record those by looking at analog meters and writing down the answers. And all that changed with the advent of digital computers. And in 1956, the first digital power flow solution was performed by J.B. Ward and H.W. Hale. And that method, or the method used, was the Gauss-Seidel method. It was a non-matrix method and had slow convergence. But that was setting the stage for even more progress to be made with digital solutions, and because we were just at the starting point. And I would say the 1960s were definitely the key years of advancement for digital power flow solutions. And those advancements, the most major advancement came from William F. Tenney of Bonneville Power Administration in 1967. Actually, even in the earlier 1960s as he was developing these methods, and then in 1967 when he released his classic papers. Bill Tenney is regarded as the father of modern day digital power flow solutions. And as I noted, two papers written in 1967 were landmark papers for power flow solutions using digital computers. The first one was the development of Newton's method and using that to solve the power flow situation by creating a matrix called the Jacobian, which was created from calculating partial differentials of the relationship between voltage and power. And that matrix was then iterated. And because it was a matrix, there were also some needs that automatically developed, and that led Tenney to develop efficient matrix techniques by which you could solve the system much faster and without as much memory. And that second paper was one of the most referenced and quoted papers in IEEE history. Tenney went on to become the head of BPA's power engineering team, and I'm certain you know many of the names of people that he worked with. Two of them in particular are Herman Dammel, who was the creator of the EMTP, or Electromagnetic Transients Program, and Edward Kimbark, who wrote a classic text on high voltage DC transmission. Now, since that time, there's been additional advancements, and that was in regards to the Newton-Raphson method. And those are two in particular, which are the decoupled method and the fast decoupled method. Both of them perform enhancements so that you would produce the solution faster and have to do less factorizations of the Jacobian matrix itself. And the decoupled method in particular, and both decoupled and fast decoupled, happen to work really well on interconnected power systems, which are well conditioned for them because of the high X/R ratio that's within those systems. After those methods in Tenney's career, he also produced the current injection method, which is not that well known. There were a couple papers written on it. The Aspen one-liner software and the Easy Power software utilize Tenney's current injection method. So combining power flow tools to widen scope is kind of one of the last things to talk about in terms of advancements, and I have a number of slides below for that. But what that is going to rely upon is something like the Python programming language. And we'll get into that to show how even these advanced power flow solution methods were enhanced even further, and their scope was expanded to perform all types and forms of analysis today that we're actually using in the power systems that we design and run. Now, one of the key things to understand about power flow is that it is not causal. In other words, it doesn't start at a particular time and then reach an end time. So if you have two conditions, like my initial condition of my power flow, and then I want to solve it to reach this new condition with a line outage. To do that, we're not going through time. In fact, what it's doing is it's jumping to the final condition and bypassing all the transient and dynamic response that would have happened over time when you took that line out of service. Thus, to reach that end goal by bypassing the time simulation, it's necessary to iterate because we are enforcing conditions on network equations. And some of those conditions that are being forced, here's a short list of a few. AVR voltage control, which takes time to respond, but yet in a power flow, we're going to assume that it is working well, and that is bringing voltage back to the set point. Constant power loads, transformer tapping, LTC, load tap changing control, capacitors and reactors switching on and off, inter-area power control, that's done in inter-area mode, and in which power is held and transferred across certain parts of the system. SVC and STATCOM VAR control, which is, has feedback controls built into them, but which maintain criteria within them in which they're going to hold voltage and hold VARs. Often for STATCOMs, there's a volt-VAR curve that's involved there. And there are many more conditions that are actually being enforced in modern day power flow solutions, but I think that's a good start for us to see. Now, to look at this iterative need that's within power flow, let's do a really quick example, all right? We're going to look at constant power loads. So imagine we have a system, 10-volt source, a 1 ohm line, we have a 10-watt load, and what we want to know is the voltage at V load, all right? The load is constant power again. So for that condition, we could start off assuming that the load voltage is 10 because we don't know what the voltage drop is yet. We know the voltage is going to be lower than 10 volts, but we don't know what it is yet. So for that condition, if we calculate I load as 10 watts over 10 volts, we get an amp. And now the voltage drop can be calculated to be 1 amp times 1 ohm, which is 1 volt. Now, this means the load voltage has dropped. 10 volts minus 1 volt, that is the voltage of the source, minus the drop is 9 volts. And that automatically leads us to see, oh, we're trying to hold constant power, so our current has to change. Our voltage has dropped, so our current is going to increase. Current now is 10 watts over 9 volts equals 1.11 amps. And this, of course, leads to updating the voltage drop again, because we now have a new current. So we are in an iterative loop of updating, and we see that. Now, if we continue with this action of updating, we find that when the voltage finally settles out, we're at 8.873, and the current is now 1.127. So the voltage is lower. This includes the drop across the 1 ohm line, and we're satisfying, well, we think we're satisfying 10 watts of constant power load. At least that's what we were trying to do. So did it happen? Let's do a quick check. 8.873 times 1.127, yes, indeed, equals 10 watts. Thus, we have solved for V load while maintaining a constant power condition. So this shows you this is one small illustration to show you that we need iterative capability to be able to solve the power flow simulation. Now, our present history is quite a bit different than it was back in the 60s, 70s, and 80s. In utilities, I would say power flow is still very relevant. It's used all over for utilities to determine conditions in their network and to perform outage calculations and to do designs in the power system. But in industrials, I find that power flow is mostly forgotten. Within technical societies, power flow has even become a kind of a thing of the past, because The papers are being written on the new, the tantalizing, the edge technology. So when new engineers enter those societies, they find that they're bombarded by papers on artificial intelligence, grid optimization, distributed energy resources, big data, etc. And there's very little focus on fundamentals. And in the industrial arena, what I've seen happen is that arc flash has basically come to dominate the industrial power arena for the last 20 years. It's become the key focus of many engineers, to the point to where many industrials have dropped their support for keeping an updated power flow model. When I worked at the company that has marketed and sold and developed the Easy Power software, during the time where arc flash was really taking off, we basically got less and less orders for the power flow solution module. It's basically the foundational model of all power system analysis, and people didn't want it. All they wanted was the short circuit, the coordination, and the arc flash. So it's really interesting how it's faded. And also losing the older generation as they've left the industry, with a lack of true mentorship, talking about how things were done in the past. What was normal, which to me, power flow simulation was a normal activity, has seemed to have become forgotten. And this may be one of the reasons why you're watching this video. It may be the question the reason why you ask the question, do I have a real need for power flow analysis? And why hire a consultant to perform this work? So this segues naturally into the relevance of power flow. Why is it relevant? And I'd like to answer that question by enumerating the needs that can be addressed, which also stem from the need to properly design an electrical system, evaluate and predict system conditions, understand and mitigate abnormal behavior, solve a crisis condition in the moment, and certainly there are others and combinations of these that we could put together. But first, before we start enumerating, what are the foundational results of a power flow? In an actual power flow simulation tool, the actual results that will be yielded from the simulation are bus voltage magnitudes and angles, and equipment real and reactive power flows, and current flows. So is that it? Yes, literally that is it. When you solve the solution, that's what you get. But remember, consider how things work in life and in electrical engineering. One thing always builds on another. So our foundation are these quantities. Now, let's expand those just a little more, because those quantities can be considered delivered to equipment, consumed by equipment, delivered to the grid, generated by equipment, flowing through equipment, wheeled across the grid, flowing through a number of equipment items, delivered from one power area to another, and more. Bus voltage magnitudes and angles can represent locations on a 500 kV grid down to 120 240 volt service panel. Hey, locations along a distribution feeder, a plant's main bus, locations within a plant, locations within a wind and solar farm collection system, or basically any location where you can model a bus between any other two pieces of electrical equipment. It's interesting, locations on a 500 kV grid versus a service panel. I've seen that diversity. I've been in a 500 kV TVA substation doing flicker measurements and walking in and just the crackling of the corona over your head and your hair is almost standing on end because of the electric field. Wow, what an experience. And then you go down to, well, in this case, I was going to a gym and measuring a 120 240 volt service panel, kind of like from the phenomenal to the mundane. But yes, a power flow solution can simulate everything from 500 kV down to 120 and 240. Now, foundational results can be expanded even a bit further. We can find or create these commonly used reports in power flow solutions. These are the ones you'll find in everyone's solution. Low voltage conditions, high voltage conditions, in other words, below a threshold, above a threshold, anything above or below will trigger a message for you or be generated in a report as being over your threshold. or under your threshold, plots of voltage along network sections or feeders, power losses. Yes, if we have the current flowing through our electrical components, we can calculate I squared R losses. Overload of equipment, transformers, lines, cables, etc. Transformer tap positions if you're simulating load tap changing transformer, and there's even a number more that are the standard reports. But I think this is a good list to show as we're expanding what those foundational results are bringing us. Okay, so now let's enumerate. What can we do with the results we've just covered? Right now might be a good time to get a pencil on a piece of paper if you want to write down what's relevant to you. This is a pretty long list, but let's start through it because you're going to find at least one thing here in this list that's going to be relevant to you. Energy loss and efficiency evaluations. Hey, you make a power factor correction, you've reduced the current flowing through your main transformer, I squared R losses are going down. You are saving energy. Tell the utility about it. You might get a rebate. So definitely in this time of green energy, efficiency and loss evaluations are important. Wind farm and solar farm reactive power requirements. These evaluations, these are being done right now, all the time. Wind farms are going in, solar farms are going in, and they have to meet reactive power requirements because they are now generating sources and are replacing conventional generation. They have to be able to hold and support voltage and supply VARs, similar to conventional generation. Evaluation of voltage collapse and steady state power transfer limits. And then this extensive line outage of analysis of N-1, N-2 contingencies. When I was at PTI, I wrote programs that controlled the power flow solution to do this. And this was before Python. The PSSE package had a programming language called IPlan, a precursor of Python. And what it did was it allowed you to control the power flow solution. And by controlling it, I could tell it how many cases I wanted to run, and then I would accumulate the results to create voltage collapse QV curves. And for the line outage, I worked with WAPA. I went out there and taught a class on iPlan, and we built and started a structure for creating a contingency analysis program for them, where they would be running hundreds and thousands of contingency cases. That can be done with PowerFlow. Both of those can be done with PowerFlow. We're going to have a couple more slides on Python in a few minutes. Evaluation of fixed and automatic tapping transformers and network voltage regulation. Those kind of go together. What if you have a fixed tap transformer and you're specifying it for a new plant or for replacement? Is it good enough? Is it going to handle the voltage regulation? Is the impedance small enough? Or do you need LTC control to basically keep your voltage at a good nominal condition to serve your load correctly? Cap bank and StatCom impacts on voltage, power factor, and regulator tapping. This one here is really critical for distribution feeders, especially today with a lot of introduction of solar sites on distribution feeders, where the generation back into the feeder causes a voltage rise. And this happens repeatedly, day after day, causing possibly excessive regulator tapping. If you want to simulate and know those conditions, you can use a power flow. Overloading evaluations, very common, and we mentioned that earlier. Power factor correction, you can do bank sizing. You can see how the power factor is improved, and you can see the reduction in the losses. Power wheeling impact on overhead lines, generators, and system voltages. If you're wheeling power across a system, you're going to be doing it over certain transmission lines, and you want to know how those are impacted when you're wheeling. Can you take that wheeling? Do the overhead lines have the capacity that they need? And how are the generators going to be loaded, and where are they going to be loaded? Loss of generation and system islanding response. The West Coast broke up into 5 pieces about 25 years ago, if you remember that event. Some transmission line in the Northwest tripped off. If you want to evaluate how each of those islands handled their voltage response across the grid with the particular generation and load condition they were left with, you can run a power flow simulation to determine that. Capacity planning for system load growth. Often in industrial power systems, we just add the loads up and say that's it. But that's not it. That's not all of it. Those loads flow through components. They flow through transformers, they flow through cables, and they will have additional real and reactive power losses. So if you want to know your total load that you're going to be having on a system for capacity planning, run a power flow simulation. Equipment sizing. Use a power flow to determine alternate switching conditions, things that might overload equipment. You can perform those in a power flow solution because these are steady state conditions that are being considered. Renewable energy impact on feeder voltage regulation. We mentioned that just previously. One of the most key things that I've used actually myself is time T0 plus switching. In this case, you need a slightly modified power flow solution that replaces the swing sources and voltage controlled sources and motors with Thevenin equivalent voltage sources. And if you have a tool that will allow you to do that, then you can simulate that moment right after the switching event, whether it's starting of a motor, whether it's switching on a capacitor bank, whether it's a sudden loss of load event. You can determine what that sudden voltage change is by doing a time T0 plus switching event. Ferrani rise and loss of load voltage rise with capacitor banks. If you have a feeder and it's lightly loaded and you didn't think it through and you didn't run a power flow case, you may have a condition where the voltage escalates to 115, 117% by the time you get to the end of the line. Alternate feeder switching impacts. What if you have a client who's an industrial who on purpose wanted to have their plant located near a substation because they wanted the stiffest bus, short circuit level they could get? In an alternate switching condition, they may be at the end of the line, right? Because they were at the beginning of the line, but if you take the substation out, they'll have to be fed through an alternate route. Can you support the voltage for that client? Can you keep it up to where it's supposed to be and what they desire, even though the short circuit strength has dropped significantly? Phase and sequence imbalance evaluations. Now, these are for three-phase unbalanced power flow simulations, which you can do in software tools like the Sine package. So here, phase and sequence imbalance evaluations, you can determine how the voltage imbalance is going to be on a distribution feeder. Can line transpositions or load reallocations on each one of the phases help you to reduce imbalance? You can simulate those conditions, of course, with a three-phase unbalanced power flow solution. And now the last three that I'd like to present, this list is not exhaustive. I mean, you can just keep going and going, and because there's so many specialty tools being developed by Python programmers today. But let's consider these last three. Long-term time simulations to reveal dynamic loading impacts, switched capacitor performance and regulator tapping performance, and dynamic equipment overloading. So consider you have a distribution feeder, and now you're going to simulate a power flow simulation that represents this loading condition, and then you go to load and you simulate another one for 5 minutes later, and then 5 minutes later. So it's a series of power flow simulations over a day that can help you determine how dynamic changes in loading are affecting switched capacitor performance, coming on, going off, coming on, going off, regulator tapping performance, and then the dynamic loading on your equipment. These are really important. The Sine package also happens to do these long-term. So they're really not real-time simulations, they're quasi long-term time simulations by using a series of power flow solutions. And now these last two key items. If you're going to do harmonic calculations or dynamic simulations, you need a power flow case. For harmonics, it's your baseline fundamental frequency loading condition. And for dynamic stability simulations, the power flow is the baseline loading condition for initializing all of your dynamic models. Now, I spoke about this while we were discussing and enumerating those items. Scope widening. So what has come on the scene now in the last 15 so odd years is the Python programming language, which has now been integrated into many power flow analysis tools and harmonic tools and stability tools and short circuit tools, depending on the providers of the software. And what it allows you to do, it allows you to increase the scope and capability of the PowerFlow tool that you're using under the hood. Some examples, the one I just talked about, about the automated contingency analysis, the work that I did for Western Area Power Administration, voltage collapse, QV and PV curves. You can write Python programs to generate these answers for you. The voltage collapse QV curves are a series of PowerFlow solutions that are one after the other while changing and updating voltage and VAR conditions. How about simulation of unmodeled long-term control actions? Maybe you have something in your plant process where the loading is changing over time. Every minute or so, or every 5 minutes, it's changing significantly. And you want to know what that's doing to your overall demand profile. You can perform these type of simulations. You can write a Python program that'll take your loading data, inject it, solve the power flow, inject the next case, solve a power flow, inject, repeat, and then you store and save the results for yourself. Also, you can automate the running of particular simulation sets that are important for you and for the types of analysis that you perform. So if there's something that you want to do that's special, but you run these 20 simulations every time that you get a particular case from a client, you can write a Python program and just push a button and it will run them, tabulate the results automatically for you, which leads to creation of specialized reports. You can pull and extract the information out of the power flow, the voltages, the flows, whatever those conditions are, you can pull them out after each case has been solved and tabulate them and save them in any particular format that you would like for yourself. And finally, basically whatever you can dream up, to improve your engineering workflow and your efficiency. So if you can dream it up, you should be able to write a Python program to do it. So PowerFlow results. What are the type of PowerFlow results we can expect in standard packages? The ones I'm going to talk about here are the most common, except for the last one. That one's kind of a specialty thing created by a Python program. Tabular reports. Yes, tables. I'm sure you'll know all about tables. We don't have to dwell on this very much. Plots of voltage and loading over distance or geography. That's important for distribution feeders. Graphical images of flows on the one-line diagram. So you get that electrical connection perspective. And then finally, this last one, graphical images of power flow capability and requirements. I'll show you that one, which requires a Python program. Now, some examples. Here's a tabular overload report for a transformer. For transformers, that is, and in the column we have the transformer ID, and then we know the rated amps, load amps, and whether it's in violation or not. Here's plot of voltage magnitude versus distance along a feeder from the substation at 0 miles out to the end of the feeder at 4.5 miles. Somewhere in the middle-ish, we have a voltage regulator. So we see the voltage drop, regulator step the voltage up, and then the voltage continues to go down after the voltage regulator. Here's a wind farm one line that has the data on it. It's obviously, we're zoomed out, it's hard to read, but if we were to run a power flow simulation and then zoom in, we could see results like this. String megawatts and megavars, per unit bus voltage and angle here. Kilowatt and kVAR losses are shown here. This particular tool and simulation allows you to put losses right on the one line. Turbine MVA and power factor are shown here for the wind turbine. Here's the turbine megawatt and megavar being delivered to the step-up transformer and the actual tap setting, on the transformer as well. This happens to be a fixed tap transformer. So this last one is the one I talked about that requires a Python program. And in this case, it requires 21 power flow cases to simulate the resulting VAR capability of the wind farm, which is in orange. And what's plotted along with it is the criteria of what's necessary for this wind farm to be connected and online and running. And that would be a 0.9 power factor producing, that's the blue curve on the right, and the blue curve on the left is 0.95 power factor absorbing. Orange, of course, is the actual performance, which is exceeding the capability and thus the criteria is met for this case. Now, power quality. So Powerside is a power quality company. How then does power flow relate to power quality? So you might have some confusion here. You say, well, I looked up Powerside because I wanted power quality information, but now I see that there's services being provided and I see that you have a video on power flow. Well, why would I want to use a power flow for power quality? So in the same way that a model simulation relates to an actual system condition, power quality and power flow are a natural reality simulation pair. For example, power quality measurements can help supply benchmarks for model validation. If you have a measurement and you know what the conditions are for voltages and flows for your pre-event condition, you can simulate in the power flow and you can match it and say that you met a benchmark. This gives you a lot of confidence when you're moving forward in your simulation work. Similarly, power quality measurements can capture conditions that need to be understood, like a power quality event. So models can then be improved and we can then use them to predict them, right? Improve the model. Now we can predict these unusual conditions that were captured by power quality measurements. Power flow simulations have the ability to predict power quality conditions for design, for what you want to mitigate with, system operation, how is it going to operate, and then finally, measurements can be brought in for measurement and verification. So again, they're working as a pair together. In general, I would say power flow simulations and power quality measurements can be used to validate each other. A couple more examples. Power flow simulations can be used to specify equipment that improves our power quality, such as putting in a capacitor bank for voltage support. You can simulate that and you can prove your power quality has improved by a power flow simulation, and then you could measure it and verify it. Power flow simulations can show why poor power quality even exists so that it can be mitigated. That's kind of like this one, where power quality measurements capture conditions that need to be understood. So once they're understood, you can show why they're there through the simulation and the model, and then perform mitigation. And here's two more to go. The second to the last one, power flow simulations can educate a user. This is important, and a lot of people may not realize you can do this with a power flow, but I use it for this purpose all the time. Power flow simulations can educate a user in the finer aspects of the vector nature of AC power systems. If you don't quite get why voltage is dipping or not dipping, run some power flow cases. Look at the conditions. Try to understand what's happening here, okay? Use the power flow to help educate yourself. And lastly, power flow simulations have a network view that can aid power quality measurements, which have a narrow field of view from a measurement perspective. And as a pair, when they're brought together, it brings greater depth and understanding to many, many power quality conditions. The power of a network and a network model, the power of a measurement, bringing them together gives you greater understanding. So in conclusion, thank you so much for attending the video, and my hope for you is that you have a greater appreciation for power flow analysis, that you'll make greater use of power flow modeling and simulations for a key reason. Yes, for a key reason, so that your engineering designs and analyses are greatly improved and that they have a firm engineering foundation. Now at Powerside, we're keenly aware of the importance of power flow analysis, and we ourselves, we utilize it to properly engineer designs in our power correction business, aid interpretation of power quality conditions in our power quality monitoring business. And overall, it's a key tool that helps us to speed our workflow, reach highly accurate and well-engineered designs, and to supply repeatable results for you. All right, well, that kind of wraps it up for this video. I'd like to thank you for attending and watching. And we do appreciate you as customers and clients, and please let us know if we can perform any services for you. I'm sure you can reach our salespeople, and they can put you in touch with our engineering staff if it's necessary. So again, thank you for watching, and please remember, be the best engineer you can be, because truly, I'll tell you, the world desperately needs you. Thank you very much.